Beth.
And I'm Beth.
Welcome to Physics with
Beth and Beth.
Hello, welcome to Physics with Beth and Beth. I'm Beth. We are in AP Physics 1 curriculum. That's that algebra-based curriculum. Unit 6, Energy and Momentum in Rotating Systems. It's a mouthful for a title. We mentioned that before in other videos this unit, but it's exactly what it is. And today we're going to be talking about that energy in rotating systems. And we're going to actually be talking about work and the Work-Energy Theorem. If you've noticed anything in Unit 5 and 6, hopefully you've noticed that we're basically going through all of the linear motion that we learned in the equations and the concepts from first semester, and now we're applying them to rotational motion instead of linear motion. All right, and so every time we do this and we start new concepts, I always start with the linear to remind us because we've mastered this. And then it helps us really get a hold to understand better and get a mental hold on what this means with rotational motion. All right, so we're going to do the same thing just like we always did. Today we're talking about work. Remember in linear, we said, hey, force was this work was this parallel force times the displacement. And it had to be parallel. Only parallel forces do work. And then we talked about that displacement. If you didn't have displacement, you didn't do work. You could push on a wall all day long till your muscles are shaking. If it doesn't move, you didn't actually do work in physics terms. All right, then we also talked about this Work-Energy Theorem, which says that work is equal to the change in kinetic energy. Whatever work you put into an object, if you have a chair and it's at rest, with a 0 initial velocity, and then you push it, you put force to it, and it starts moving, you have added energy into that system through the work of your push. All right, and that's what this says, that the change in kinetic energy, remember kinetic energy was 1/2 mv squared. So we have 1/2 mass times final velocity squared minus 1/2 mass times initial velocity squared. And that's going to equal that force that you put into the chair times its displacement. And then you can figure out what the final velocity of that chair is if we use that chair as an example. And all I did was say, hey, work's equal to the change in kinetic energy, work's equal to that parallel force times displacement. So I set those equal to each other. And we have this great equation that is very, very handy dandy. All right. The other thing that's worth noting, I've already got a video out on power and angular motion or rotational motion, but it's worth noting here because we did talk about work, the Work-Energy Theorem, and then power all in the same time when we were doing linear motion. So just remind yourselves, power is work divided by time, that change in time, that time interval. Well, power then is that work, that parallel force, times displacement over that time interval. And then if we remember, velocity is the displacement divided by that time interval. So I just took this little expression right here and replaced it with velocity. So power is force times velocity. All right, so that's kind of a nice little thing to remember. We're just reminding ourselves since we did that in this unit. Okay, now let's go to rotational. Now work in rotational is actually torque times your angular displacement. So we're replacing force for torque, and torque is always going to be that perpendicular force, if you remember that. And then we have our angular displacement. So it looks pretty similar. All right, this is actually going to be, remember a torque is a Newton times a meter, and theta is just radians, so it's a Newton meter. Okay? All right, perfect. Now, let's go to this work equals kinetic energy. It's the same thing for rotational, but work equals that change in kinetic energy rotational, which my students like to call it caret or K-rot. But anyway, that was our little made-up little term for it, but that rotational kinetic energy. Okay, well, what does rotational kinetic energy look like? We said, hey, kinetic energy in rotational is 1/2, not 1/2 mv squared, which it was here in linear. In angular, it's 1/2 I times that moment of inertia, or rotational inertia, times that angular velocity squared. All right, so I'm going to put these together. I'm going to say, hey, torque times delta theta, or your torque times your angular displacement, equals 1/2 times your moment of inertia times that final angular velocity squared, because it's this change in kinetic energy, minus, because remember our delta always means final minus initial, change in, 1/2 moment of inertia, angular initial velocity squared. All right, and now we have what it looks like in rotational. I just feel like it's always helpful to see these side by side. And remember that for mass, you know, we're subbing in that moment of inertia. It's not exactly the same thing, but it's equivalent in rotational. And then velocity, we're subbing in angular velocity. For displacement, we're subbing in angular displacement. For force, we're subbing in that torque. Remember, those aren't exactly the same, but they're comparable for rotational motion. And that helps you remember these formulas better and to understand. Okay, now one more. I would like to step over here in power. Remember, power, if we had work divided by time, it's the same thing. Work divided by time, that time interval. Well, now work is tau, well, some people say tau, but it's torque is what it represents, times angular displacement. So I'm going to put that in. I'm going to say, hey, that's torque times angular displacement over time. All right, all I did was sub in this little expression for my work right here. Oh, well, wait a minute. We remember that angular velocity is angular displacement over our time interval. So look, we can sub that in for here. And we end up power equals torque times that angular velocity. And you now have we've already done a video on this, and I've already posted it, but that's where that comes from. I don't think I derived where that came from, and sometimes it's helpful to see that, especially laid out by linear. Okay, now let's just get started. We have a problem. Very lengthy problem, but here we go. A 55 Newton force is applied to the edge of a 5 kilogram disc with a radius of 0.35 meters for 4 seconds. So the force is applied to the edge of this disc for 4 seconds. The disc has an initial angular velocity of 6.5 radians per second, which means it's already spinning, and it's spinning counterclockwise. That's why it's positive here. And they want to find the work done by the force and the angular displacement of the disc. All right, let's just get going with what we have. We always start at across when we're trying to identify our variables, and we say, hey, we have a 55 Newton force, and that is perpendicular. How do I know that? And that's a 5. It's not a very good 5. We have a disc here. We have a force being applied of 55 newtons. It's going to be perpendicular to that radius of 0.35, and it's on the edge. So it's applied 0.35 meters from the axis of rotation, that force. All right, we know the mass of the disc is 5 kilograms. We know that its initial velocity is 6.5 radians per second. We also know that time is 4 seconds that force is applied. And what else do we know? The radius is 0.35 meters. And I think that's all we have initially. All right, so we got to get started. They want work first. I'm like, okay, work is equal to, this is all linear, so now we're looking here, and I'm actually going to go ahead and erase this so we have a little bit more room. Pause that, back it up a little bit and pause it. If you need to see that again, we're just going to erase all this so we have some more room to work other parts here in a minute. Okay, so we want work. Okay, well, we know work is torque times delta theta. Work is also the change in kinetic energy rotational. All right, I know I'm asked for find both of these. So I'm not picking this equation to start with because I'm going to have two variables I don't know. How do I know that? Because they ask for work and they ask for angular displacement. So that formula is going to be a little hard. That equation is going to be a little hard for me with two unknowns to find one or the other. All right, so I'm going to go, okay, well then I'm going to go with this work equals this change in rotational kinetic energy. That's a mouthful. All right, so work is equal to that change in kinetic energy rotational. And I'm going to say, okay, well, I know what that is. It's 1/2 that moment of inertia times angular final velocity squared minus 1/2 times rotational inertia, means same thing, initial velocity squared. I'm like, okay, so first, I don't have a lot of things here. I don't have my final. I don't have my moment of inertia. I do have this, check, I have that over there. But wait a minute, can I find these? Absolutely you can. All right, so how am I going to do that? Well, first I know that the moment of inertia of a disk, because they said this was a disk, is 1/2 m r squared. All right, so that's 1/2, mass is 5, the radius is 0.035, that's going to be squared, only that's going to be squared. And my I is 0.36, that's not, yeah, 30625, sorry, I had to cheat and look down below. Kilograms times meter squared. So I have my I. Now I'm not going to box that, but I need that information. Okay, that's my moment of inertia. Check, did that. All right, I know my initial. How can I find my final angular velocity? Just like when you were working with work and energy before, we had to sometimes throw in those big three. All right, well, we have the big three for rotational motion as well. All right, those kinematic equations, we have them for rotational. And they're in an earlier video. If you haven't seen that, you can look back in this in Unit 5, actually, is where that video is. But I'm gonna know this. I'm gonna kind of square this off here so I give myself a little space. I know that my torque, the sum of my torques equal that moment of inertia times my angular acceleration. What is that? Well, that's Newton's second law, but for rotational motion. And again, that is in Unit 5 if you haven't seen that video. But that is just second law, but for rotational motion. I'm like, okay, wait, I know my I. My I was 0.30625. And if I knew my torque, I could find my angular acceleration. If I could find my angular acceleration, I'm going to be golden, because then I can use, I'll come down here, I can use my final angular velocity equals initial angular velocity plus angular acceleration times time. That's the first of the kinematics. In linear, it looked like final velocity equals initial velocity plus acceleration times time. I have time, I know my initial, and if I can find this angular, then I'm great. And I can now then plug that in here. We have all of our numbers, and we are home free on figuring out this work. But we need torque, right? I need the sum of my torque. Okay, well, there's only one force applied. It's this 55 Newton force, and it's applied with an R. Remember, torque is R times that perpendicular force. We already said it was perpendicular, so torque is R, which is 0.35, not 0.35, 0.35 times 55. And that torque is going to be 19.25 Newton meters. Oh, now I have torque, 19.25 meters. I divide 19.25 by moment of inertia, and I'm going to get angular acceleration of 62.857 radians per second squared. Okay, now I can plug that in to find my final velocity. My initial was 6.5, we said. My angular velocity is 62.857. And my time was 4 seconds right here, times 4. And my final angular velocity then is 258 radians per second. Now I can plug that in down here with my moment of inertia, and voila, we did it. All right, so that's going to be 1/2 times my I was 0.30625. My final angular is 258. It really comes out to, I think, 257.9. I'm rounding it up there to 3 sig figs. And that is squared. Do not forget to square that. It is such a shame if you go through this whole problem and forget a square and get the wrong answer. It's just kind of gut-wrenching, actually, when you do that. All right, 0.30625, and my initial was 6.5 squared. All right, then you're gonna have work is gonna equal 10,186 joules. And you have just figured out work. Let's go back through that though, because this is one of those problems where there's so many steps to this that you have lost what you're even solving for. So let's go back through and do this again. First of all, we had 2 options to find work. But I didn't choose the first one because the problem has asked for work and angular displacement. They're both in this equation together, and I feel like I'm really going to have to find one and then solve for the other, but I can't use this equation because there's two unknowns. So I went with work equals the change in kinetic energy rotational, or that rotational kinetic energy, which was 1/2 moment of inertia, angular final velocity squared minus 1/2 rotational inertia times angular initial velocity squared. I'm like, oh, okay, wait a minute. I got my initial. I can find I easy enough. Moment of inertia, it's a disk. So it's 1/2 mr squared. I put in the mass of the disk and the radius, and I got my I, so I was golden on both of those. Now I only had one variable left to figure out, and that was my final angular velocity. And I'm like, oh, probably can use some of the kinematics. So I go back to the kinematics, and I say, okay, torque equals that moment of inertia times angular acceleration, Newton's second law for rotational motion. I found my torque because I knew my R value, and they told me that perpendicular force was 55. So I had my torque, easy peasy. I already knew my I. Moment of inertia, I solved for my angular acceleration, and then I used my first kinematic equation, that angular velocity final equals initial angular velocity plus acceleration times time, angular acceleration times time. So my time was 4 seconds. I just solved for angular, and I had my initial velocity, and I got 258 radians per second. So that completed my last unknown of this little equation of work equals change in kinetic energy, and I came up with work. So yay, almost done. Now it says, hey, find angular displacement. Okay, that's much easier because we know work equals torque times angular displacement. I just found my work. I already found my torque. It was up here, 19.25 times delta theta, and I can solve for that, and my delta theta equals, oh, I do not have it down here. My delta theta equals 529.15 radians. If you want to divide that by 2 and then divide by pi, you're going to get revolutions, which is 84.2 revs. However they'd asked for that answer. All right, that's it. That's the problem. It combines, we've talked about work, right here, we talked about work in rotational motion, how the work equals the change in rotational kinetic energy theorem. And then we have a great equation here to use. There you go. And how you can actually pull in Newton's second law and our rotational kinematic equations, all to do this, what seemed like a pretty simple problem when you sat down to start it. All right, I hope that helps. Hang in there. If you have followed this, I always tell my students this time of year, if you have followed this, pat yourself on the back, because if you remember way back in August or whenever your school year started for this material, if you remember, somebody had shown you this board at the very beginning of this course, you might have ran away screaming. All right, but so if you followed this, give yourself a pat on the back. You are doing awesome, and you've got this, and we are almost done with this curriculum. Just 2 more units to go. You can do it. And thank you for watching. If you like this, please hit a like. If you haven't subscribed, we would love for you to do that. We would love to know that we have people out there that we're helping. So anyway, and pass it on to your peers if they're also struggling. We're here to help. Thank you for watching, and happy physicsing.